Dear listener, hello and welcome. Tonight, we gently turn our attention upward to the vast and quiet sky that unfolds while you sleep, a place filled with distant light, slow motion, and stories written across unimaginable distances where every point of light carries a history far older than memory itself. The night sky holds objects so distant that their light has been traveling for millions or even billions of years before reaching Earth. When you look upward, you are not seeing things as they are now, but as they once were long ago, preserved in motion. This means that the sky above you is a layered archive of time. Each star, each faint glow, represents a different moment in cosmic history, arriving together in a quiet, unified display. Some of the faint smudges visible under very dark skies are not stars at all, but entire galaxies. Each of these galaxies contains billions of stars, all bound together by gravity. Even though they appear small and distant, their scale is immense. What seems like a faint blur to the eye can actually be a structure larger than our own galaxy. The Milky Way itself stretches across the sky as a soft, luminous band. It is composed of countless stars so distant and numerous that they blend into a continuous glow. This glowing arc is not a cloud or mist, but the combined light of stars packed densely within our galaxy's disk, forming a structure that surrounds us. The brightness of some objects in the night sky can exceed that of all surrounding stars combined. Planets like Venus can shine so intensely that they cast faint shadows under dark conditions. This brightness comes not from their own light, but from reflected sunlight. Their proximity and reflective surfaces make them stand out vividly against the darker background. Some stars visible at night are far larger than the Sun, known as supergiants. If placed at the center of our solar system, they could extend beyond the orbit of planets like Mars. Despite their enormous size, they appear as small points due to their great distance. Their true scale becomes clear only through careful measurement. The color of stars can vary subtly, ranging from blue-white to deep red. These colors indicate differences in temperature, with blue stars being hotter and red stars cooler. Although the human eye perceives most stars as white, under ideal conditions, these color differences can be faintly distinguished. Occasionally, the night sky is streaked by meteors, brief flashes of light caused by small particles burning up in Earth's atmosphere. These streaks are often called shooting stars. Despite their name, they are not stars at all, but fragments of cosmic debris. Their sudden appearance and disappearance add a dynamic element to an otherwise steady sky. At certain times of the year, meteor showers occur, producing multiple streaks in predictable patterns. These events happen when Earth passes through trails of debris left by comets. The particles enter the atmosphere at high speeds, creating glowing trails that last only moments but repeat in quiet succession. Some stars pulse in brightness over time, gradually growing brighter and dimmer in repeating cycles. These are known as variable stars. Their changes can be caused by internal processes or interactions with companion stars, offering insight into stellar behavior. The moon, when present, dominates the night sky with its brightness. Its surface reflects sunlight, making it the most noticeable object after sunset. Even though it appears large and luminous, its surface is relatively dark. Its brightness is due to its closeness compared to distant stars. The moon can appear larger when it is near the horizon, an effect known as the moon illusion. This is not a physical change, but a perceptual one created by the brain. As it rises higher, it returns to its normal apparent size, revealing the illusion as a product of human perception rather than astronomy. The sky contains stars that move in slow arcs over the course of the night. This motion is caused by Earth's rotation, giving the impression that the sky itself is turning. Over hours, these arcs can be observed as stars rise, travel, and set, following predictable paths across the sky. Long exposure photography reveals these movements as continuous circles known as star trails. These trails form concentric patterns around the celestial poles. They visually capture the steady rotation of Earth, turning motion into visible patterns of light. Some stars never set below the horizon, known as circumpolar stars. They circle the sky continuously without disappearing. Their constant presence depends on latitude, with more stars becoming circumpolar closer to the poles. The Andromeda Galaxy, visible under dark conditions, is the nearest large galaxy to the Milky Way. Its light has traveled about 2.5 million years to reach Earth. Seeing it means observing a structure as it existed long before modern humanity, preserved in faint, distant light. Comets occasionally appear in the night sky with glowing tails stretching across space. These tails form as sunlight and solar wind interact with the comet material. The tails always point away from the sun, creating long, luminous shapes that can be visible for extended periods. Some stars are part of binary systems, orbiting a shared center of mass. These systems can consist of two stars closely bound by gravity. Their interactions can affect brightness, motion, and even the evolution of each star over time. In rare cases, stars end their lives in powerful explosions known as supernova. These events can briefly outshine entire galaxies. The remnants of such explosions continue to glow for long periods, leaving behind expanding clouds and dense cores. At the center of our galaxy lies a supermassive black hole. Though invisible, its presence is revealed by the motion of nearby stars. These stars orbit rapidly around an unseen point, indicating a massive gravitational source. The sky includes faint clouds of gas and dust known as nebulae. Some glow brightly, while others appear as dark silhouettes against the Milky Way. These regions are often sites of star formation, where new stars are born over long timescales. There are stars so small and faint that they cannot be seen without instruments. Red dwarfs, for example, are common but dim. Despite their faintness, they are among the most numerous stars in the galaxy and can exist for extremely long periods. The night sky is not entirely dark, even in remote locations. A faint glow known as air glow comes from chemical reactions in the upper atmosphere. This subtle light adds a gentle background brightness, barely visible but always present. The light from distant galaxies is stretched as the universe expands, shifting toward longer wavelengths in a process called redshift. This stretching provides evidence that the universe is not static, but continuously expanding over time. Some objects in the night sky are moving at speeds great enough to escape their galaxies. These hypervelocity stars travel through space at extreme velocities. Their motion reflects powerful gravitational interactions, often involving black holes. The night sky includes objects emitting invisible radiation, such as X-rays and radio waves. These signals reveal energetic processes not seen in visible light. Different wavelengths allow scientists to observe the universe in multiple ways, uncovering hidden structures. Even when clouds cover the sky, the stars remain above, continuing their motion unchanged. Their presence is constant, regardless of visibility. The sky's activity does not pause, even when unseen, maintaining its quiet, continuous rhythm. The light from stars is affected by Earth's atmosphere, causing them to twinkle. This effect is more noticeable when stars are low in the sky. Planets, by contrast, usually shine more steadily because their apparent size reduces the impact of atmospheric distortion. The night sky contains faint dust that reflects sunlight, creating a soft glow known as zodiacal light. This glow can appear as a subtle triangular shape along the horizon, under very dark conditions. Some stars are so dense that their remnants form neutron stars. These objects compress mass into extremely small volumes. Their density is so high that matter behaves in unusual ways under intense pressure. Pulsars, a type of neutron star, emit beams of radiation that sweep across space. When aligned with Earth, they appear as regular pulses of light. Their precise timing makes them among the most consistent natural signals in the universe. The sky includes galaxies interacting and merging over long periods. These interactions reshape their structure and trigger bursts of star formation. Though slow on human timescales, these processes are ongoing throughout the universe. The entire solar system is moving through the Milky Way, orbiting its center over hundreds of millions of years. This motion means that even the background of stars changes gradually over vast timescales. The night sky represents a combination of countless distances, times, and energies. Every point of light carries a unique origin. Together, they form a quiet, expansive view that continues to unfold, moment by moment, far beyond immediate awareness. The night sky stretches far beyond the boundaries of our own galaxy, extending into a universe filled with countless other galaxies, scattered across immense distances. Each of these galaxies contains billions or even trillions of stars, forming vast systems that are separated by spaces so large that light itself takes millions or billions of years to cross them. Even though these galaxies are separated by unimaginable distances, their light reaches Earth and becomes part of the quiet background of the night sky. What appears as darkness between stars is, in reality, filled with distant structures that are simply too faint to be seen without instruments. The Milky Way is only one galaxy among many, yet it is large enough to contain hundreds of billions of stars. Its structure is shaped like a flattened disk with spiral arms that extend outward from a dense central region. Within this structure, stars are not evenly distributed. Some regions are densely packed with stars and glowing gas, while others are more sparse, giving the galaxy its textured and uneven appearance when viewed from within. The solar system is located within one of the Milky Way's spiral arms, known as the Orion Arm. This position places Earth within a relatively calm region compared to the crowded galactic center. From this location, the night sky appears as a mix of nearby stars and distant galactic structures, all layered together into a single view. The center of the Milky Way is located in the direction of the constellation Sagittarius. This region is rich in stars, gas, and dust, making it one of the brightest parts of the galaxy when viewed under dark skies. However, much of this region is obscured by interstellar dust, which blocks visible light and hides the dense core from direct observation. Galaxies are not randomly scattered, but are arranged in large-scale structures such as clusters and superclusters. These groupings form a cosmic network that spans the observable universe. Between these clusters lie vast regions known as voids, where relatively few galaxies exist. This contrast creates a web-like pattern of matter across cosmic scales. Galaxy clusters can contain hundreds or thousands of individual galaxies bound together by gravity. These clusters are among the largest structures in the universe. The gravitational pull within clusters can influence the motion of galaxies, causing them to orbit, collide, or merge over long periods. Superclusters are even larger groupings of galaxy clusters. They form extended regions of high density within the cosmic web. These structures can span hundreds of millions of light years, making them some of the most expansive known features in the universe. The observable universe is limited by the distance light has traveled since the beginning of cosmic expansion. Beyond this limit, light has not yet had time to reach Earth. This boundary defines what can be seen from our perspective, even though the universe may extend far beyond it. The expansion of the universe means that galaxies are moving away from each other over time. This motion is not due to galaxies traveling through space, but rather space itself expanding. As space expands, the distances between galaxies increase, stretching the fabric of the universe. The farther away a galaxy is, the faster it appears to be receding. This relationship is known as Hubble's law and forms a key part of modern cosmology. By measuring this motion, scientists can estimate distances and understand how the universe evolves. Light from distant galaxies is shifted toward longer wavelengths due to expansion. This shift, known as redshift, changes how the light is observed. Redshift provides evidence for the expansion of the universe and helps determine how far away objects are. The universe contains a vast amount of matter that does not emit or reflect light, known as dark matter. It cannot be seen directly, but reveals its presence through gravitational effects. Dark matter plays a crucial role in holding galaxies together and shaping large-scale structures. Dark energy is thought to drive the accelerated expansion of the universe. Unlike gravity, which pulls matter together, dark energy causes space to expand more rapidly. Its nature remains one of the greatest mysteries in modern science. The cosmic microwave background is a faint radiation that fills all of space. It is a remnant from an early stage of the universe's history. This radiation provides a snapshot of the universe when it was much younger, offering clues about its origin and development. The temperature of this background radiation is extremely low, only a few degrees above absolute zero. It is nearly uniform across the sky. Small variations in this temperature reflect tiny differences in density that eventually led to the formation of galaxies. The Milky Way is part of the small group of galaxies, known as the Local Group. This group includes the Andromeda Galaxy and several smaller galaxies. These galaxies are gravitationally bound and move together through space. The Local Group itself is part of a larger structure known as the Virgo supercluster. This places our galaxy within a hierarchy of increasingly large cosmic structures. Each level of this hierarchy adds to the complexity of the universe's organization. The Andromeda Galaxy is approaching the Milky Way and is expected to merge with it in the distant future. This event will take billions of years to unfold. Although dramatic on a cosmic scale, the vast distances between stars mean that direct collisions between stars are unlikely. Galactic collisions can trigger bursts of star formation by compressing gas and dust. These interactions reshape galaxies over time. The resulting structures can be very different from the original galaxies, forming new shapes and patterns. The night sky includes galaxies of different types, such as spiral, elliptical, and irregular. Each type reflects different formation histories and characteristics. Spiral galaxies contain rotating arms, while elliptical galaxies are more uniform in shape, and irregular galaxies lack a defined structure. Spiral arms are regions where new stars are actively forming. They contain gas, dust, and young, bright stars. These regions stand out because of their brightness and ongoing activity compared to older parts of the galaxy. Elliptical galaxies are dominated by older stars and have little gas for new star formation. They appear smoother and less structured. Their lack of active star formation gives them a more uniform appearance. Irregular galaxies often result from gravitational interactions or collisions. Their shapes can be distorted and chaotic. Despite this, they can contain regions of intense star formation. The universe contains more galaxies than can be counted individually with current technology. Deep surveys reveal billions of galaxies within observable limits. Each of these galaxies contributes to the overall light and structure of the night sky. Some galaxies host extremely bright centers known as active galactic nuclei. These regions are powered by supermassive black holes. Material falling into these black holes releases vast amounts of energy, making the centers glow intensely. Quasars are among the brightest objects in the universe and are powered by such active galactic nuclei. They can outshine entire galaxies. Although not visible to the naked eye, they are part of the distant universe connected to the night sky. Gravitational lensing occurs when massive objects bend the path of light from more distant sources. This can magnify or distort the appearance of galaxies. It allows astronomers to observe objects that would otherwise be too faint or distant. The cosmic web describes how galaxies are arranged in filaments connected by gravity. These filaments form a network across the universe. Between them lie large voids, creating a pattern that resembles a vast three-dimensional web. The distribution of matter in the universe is not uniform. Some regions are densely packed, while others are nearly empty. This uneven distribution reflects the influence of gravity over billions of years. The night sky includes radiation from objects at many different distances and times. This mixture creates a complex and layered view. Every direction in the sky points to a different region of space and a different moment in cosmic history. The universe has evolved over billions of years, from a hot, dense state to its current form. This evolution continues today. Galaxies, stars, and other structures are still forming and changing over time. The scale of the universe is so vast that distances are measured in millions and billions of light years. These units help describe the immense separations between objects. Even at the speed of light, traveling these distances would take longer than human lifetimes by enormous margins. The night sky represents only a small portion of the universe that can be observed. Much lies beyond current detection limits. Advances in technology continue to expand what can be seen, revealing more of the cosmos. The universe is governed by physical laws that apply across all scales. These laws determine how matter and energy behave. From the motion of galaxies to the formation of stars, these principles shape everything in the night sky. The night sky is a reflection of both local and distant structures. Nearby stars and distant galaxies appear together in a single field of view. This combination creates a sense of depth, even though it is not immediately apparent to the eye. The sky remains constant in its large-scale structure, even as individual objects move and evolve over time. This stability provides a consistent backdrop for observing long-term changes. The night sky continues to expand in our understanding as new observations are made. Each discovery adds to the overall picture of the universe. What is seen today is part of an ongoing process of exploration and learning. The night sky contains regions where stars are actively being born within vast clouds of gas and dust, known as stellar nurseries. These regions form when gravity causes dense pockets of material to collapse inward, gradually increasing in temperature and pressure. Over time, this collapse leads to the formation of a protostar, a young stellar object that continues gathering mass. As the core becomes hot enough, nuclear fusion begins, marking the birth of a new star. Not all stars form at the same rate or size. Massive stars gather material quickly and begin fusion sooner, while smaller stars take longer to form and evolve more slowly. This difference in formation speed influences the entire life cycle of a star, determining how long it will exist and how it will eventually end. Young stars are often surrounded by disks of gas and dust, known as protoplanetary disks. These disks contain the building material for planets, moons, and other small bodies. Within these disks, particles collide and gradually stick together, forming larger structures over millions of years through a process known as accretion. Planet formation is not uniform and can produce a wide variety of outcomes. Some systems develop large gas giants, while others form smaller rocky planets. The arrangement of these planets depends on conditions such as temperature, available material, and the influence of the central star. Over time, the leftover debris in a planetary system can form belts of asteroids or icy bodies. These remnants provide insight into the early stages of system formation. They also serve as sources for comets and meteorites that may later appear in the night sky. Stars spend most of their lives in a stable phase known as the main sequence. During this time, they fuse hydrogen into helium in their cores, producing energy that radiates into space. This balance between gravity pulling inward and fusion pushing outward allows stars to remain stable for long periods. As stars exhaust their hydrogen fuel, they begin to change. Their cores contract while their outer layers expand, transforming them into red giants. This stage marks a significant shift in a star's structure and energy output. Red giant stars can grow to enormous sizes compared to their earlier state. Their outer layers become cooler, giving them a reddish appearance. Despite this cooler surface, they can be very luminous due to their large size. Eventually, stars like the Sun shed their outer layers, creating expanding shells of gas known as planetary nebulae. These structures glow as they are illuminated by the remaining core. The core left behind becomes a white dwarf, a dense object that slowly cools over time. White dwarfs no longer produce energy through fusion. Instead, they emit residual heat, gradually fading over billions of years. Their small size and high density make them unique among stellar remnants. More massive stars follow a different evolutionary path. After exhausting their fuel, they can undergo a dramatic collapse, leading to a supernova explosion. This explosion releases enormous energy and disperses elements into space. The material expelled by supernova enriches the surrounding interstellar medium with heavier elements. These elements become part of future stars and planets. This cycle connects generations of stars through shared material. The core of a massive star can collapse into a neutron star after a supernova. These objects are incredibly dense, with matter packed tightly together. Their gravity is strong enough to compress atoms beyond ordinary states. In some cases, the collapse continues further, forming a black hole. This occurs when the mass of the core exceeds a certain threshold. Black holes represent regions where gravity is so intense that not even light can escape. Star formation and death are ongoing processes within galaxies. New stars continue to form even as others reach the end of their life cycles. This constant cycle contributes to the evolving structure of the galaxy. Over time, star clusters can disperse as gravitational interactions pull stars apart. What begins as a tightly grouped cluster gradually spreads out. Eventually, these stars become part of the general stellar population of the galaxy. Globular clusters, however, remain tightly bound for long periods. These dense collections of stars orbit the galaxy's center. They are among the oldest structures in the galaxy, containing stars formed early in its history. Galaxies themselves evolve through interactions and mergers. Smaller galaxies can be absorbed by larger ones, contributing their stars and gas. This process helps shape the size and structure of galaxies over time. The Milky Way has likely grown through such mergers, incorporating smaller galaxies into its structure. Evidence of this can be seen in stellar streams. These streams trace the paths of past interactions. The solar system formed from a collapsing cloud of gas and dust about 4.6 billion years ago. This cloud flattened into a rotating disk as it collapsed. The central region became the Sun, while the surrounding material formed planets and other objects. Over long periods, planetary systems can change due to gravitational interactions. Orbits can shift, and objects can be ejected from the system. These changes contribute to the dynamic nature of planetary systems. The Kuiper Belt contains icy bodies that formed in the outer regions of the solar system. These objects remain relatively unchanged since their formation. They provide clues about conditions in the early solar system. The Oort cloud is thought to be a distant reservoir of comets surrounding the solar system. It may extend far beyond the visible planets. Comets from this region can enter the inner solar system over long timescales. Comets themselves evolve as they approach the Sun. Their icy surfaces sublimate, releasing gas and dust. This process creates the visible coma and tail that can be seen from Earth. Asteroids can also change over time due to collisions and gravitational interactions. These processes can alter their shapes and orbits. Some asteroids are remnants of larger bodies that broke apart. The evolution of stars and planetary systems is influenced by their environment. Nearby stars, gas clouds, and gravitational forces all play a role. These interactions can affect formation, stability, and long-term behavior. The universe itself has evolved from a hot, dense state to its current form over billions of years. This process began with rapid expansion. Over time, matter cooled and began to form structures. The first stars formed from simple elements like hydrogen and helium. These early stars were often massive and short-lived. They produced heavier elements that later became part of new stars and planets. As generations of stars formed and died, the chemical composition of the universe changed. Heavier elements became more common. This process allowed for the formation of rocky planets and complex structures. Galaxies evolved alongside these changes, forming new stars and interacting with one another. Their shapes and sizes changed over time. This ongoing evolution continues to shape the universe. The night sky reflects this long history of formation and change. Each object represents a stage in an ongoing process. From young stars to ancient galaxies, the sky contains a timeline of cosmic evolution. Even now, new stars are forming, and old stars are fading. The balance between creation and decay continues. This quiet progression unfolds continuously, far beyond immediate perception. The structure of the night sky is shaped by the way Earth is oriented in space, particularly through its axial tilt of about 23.5 degrees. This tilt determines how different regions of the sky become visible throughout the year, changing the height and path of stars across the horizon. Because of this, certain constellations rise higher during specific seasons, while others remain low or disappear entirely for months. The sky you see is always shifting in response to this steady, angled orientation of the planet. Earth's axis is not fixed in place, but slowly wobbles over time in a motion known as precession. This movement takes approximately 26 J00 years to complete a full cycle. As precession occurs, the position of the celestial poles gradually shifts, changing which star appears closest to the pole over long periods. This slow change means that Polaris has not always been the North Star, and will not always remain so. In ancient times, different stars occupied this position. In the distant future, another bright star will take its place, showing how even the most stable points in the sky evolve over time. The celestial equator is an imaginary extension of Earth's equator projected onto the sky. It divides the sky into northern and southern halves. Objects located near this line are visible from a wide range of latitudes, making them accessible to observers across much of the world. The ecliptic is another important reference line, marking the apparent path of the Sun across the sky over the course of a year. It also defines the general path along which the planets move. This alignment occurs because the planets orbit within a relatively flat plane, creating a shared band across the sky. The intersection of the celestial equator and the ecliptic defines key points such as the equinoxes. These points are used as reference markers in celestial coordinate systems. They help astronomers track positions and motions with precision over time. The night sky can be described using coordinate systems similar to latitude and longitude on Earth. These systems allow precise mapping of celestial objects. Right ascension and declination are commonly used to define positions on the celestial sphere. The zenith is the point directly overhead for an observer. It represents the highest point in the sky relative to their position. Objects passing near the zenith are seen through less atmosphere, often appearing clearer and brighter. Opposite the zenith lies the nadir, a point directly beneath the observer. While not visible, it completes the vertical axis used in celestial mapping. Together, these reference points define orientation in three-dimensional space. The horizon acts as a boundary between the visible sky and the portion hidden by Earth. Its position changes depending on elevation and terrain. At higher altitudes, the horizon extends farther, allowing a slightly larger portion of the sky to be observed. The apparent motion of stars across the sky follows predictable arcs due to Earth's rotation. These arcs are part of circular paths centered on the celestial poles. This motion creates a sense of rotation in the sky, even though it is the Earth that is turning. Stars near the celestial poles move in smaller circles, while those farther away trace larger arcs. This difference is due to their relative position on the celestial sphere. The geometry of this motion can be observed through long-term tracking or time-lapse photography. The night sky's structure is also influenced by Earth's orbit around the Sun. As Earth moves along its orbit, the nighttime side faces different directions in space. This causes different constellations to appear at different times of the year. The duration of night and day changes with the seasons due to Earth's axial tilt. Longer nights in winter allow more extended observation of the sky. Shorter nights in summer limit how long stars are visible. Atmospheric conditions play a major role in how the night sky appears. Factors such as humidity, temperature, and air stability affect clarity. Turbulence in the atmosphere causes stars to twinkle, distorting their light as it passes through layers of air. Refraction in the atmosphere bends light, altering the apparent position of objects. This effect is strongest near the horizon. As a result, celestial objects can appear slightly higher than their true geometric position. The atmosphere also scatters light, influencing the color and brightness of the sky. This scattering is responsible for the faint glow that persists even at night. It also contributes to the reddening of objects near the horizon. Airglow is a natural emission of light from the upper atmosphere caused by chemical reactions. It creates a subtle, continuous brightness. This faint glow is present even in the absence of moonlight or artificial light. The presence of dust and particles in the atmosphere can affect visibility. These particles scatter and absorb light, reducing clarity. Events such as volcanic eruptions can introduce additional particles, altering the appearance of the sky. Light pollution from human activity significantly impacts the visibility of the night sky. Artificial lighting brightens the sky and obscures faint objects. In heavily lit areas, only the brightest stars and planets remain visible. Dark sky locations, far from artificial light, provide the best conditions for observing faint celestial objects. In such places, the Milky Way becomes clearly visible. These environments allow the full richness of the night sky to be experienced. The structure of the Milky Way influences the distribution of stars in the sky. More stars are visible along the galactic plane. This creates the bright band that stretches across the sky under dark conditions. Dark dust lanes within the Milky Way obscure light from stars behind them. These regions appear as gaps or shadows within the glowing band. They are not empty, but filled with dense material. interstellar gas and dust form large clouds that shape the structure of the galaxy. These clouds can collapse to form new stars. They are essential components of the galactic ecosystem. Magnetic fields within the galaxy influence the movement of charged particles. These fields interact with gas and dust, affecting structure and dynamics. They play a subtle but important role in shaping cosmic environments. The solar system is embedded within this galactic structure, moving along with the Milky Way's rotation. This motion carries it through different regions over time. Although slow on human scales, this movement contributes to long-term changes in the sky. The heliosphere surrounds the solar system, created by the solar wind. It forms a boundary between solar influence and interstellar space. This region interacts with incoming cosmic material. The interstellar medium is not empty, but filled with gas, dust, and energetic particles. These components influence star formation and galactic structure. They form a continuous environment between stars. Gravitational forces shape the motion of objects at all scales in the night sky. From planets to galaxies, gravity determines how structures form and evolve. It is the primary force governing cosmic organization. The balance between gravity and other forces, such as radiation pressure, affects the stability of systems. This balance determines whether structures collapse or remain stable. It plays a role in star formation and stellar life cycles. The night sky is also influenced by the distribution of dark matter. This invisible component affects the motion of stars and galaxies. Its presence is inferred through gravitational effects. The cosmic web, composed of filaments and voids, defines the large-scale structure of the universe. Galaxies are arranged along these filaments. This structure has developed over billions of years through gravitational interactions. The night sky is shaped by processes occurring across many scales simultaneously. Local conditions and distant structures combine to create the overall view. This layered complexity is part of what defines the sky's appearance. Even when the sky appears still, these structural processes are ongoing. Motion, interaction, and change continue at all levels. The quiet appearance of the night sky reflects a balance of dynamic forces operating across vast distances. Within the night sky, many processes occur at a medium scale where individual objects begin to interact with their surroundings in more noticeable ways. One of these is the exchange of energy between stars and the gas around them, which can heat nearby regions and influence how matter behaves. These interactions can gradually change the temperature and density of surrounding material, shaping the formation of future stars and altering the structure of nearby space. Interstellar dust plays an important role in how light travels through space. Tiny particles scattered between stars absorb and scatter light, especially shorter wavelengths. This causes distant stars to appear dimmer and slightly redder than they truly are, an effect known as interstellar reddening. Gas clouds in space can compress under the influence of nearby stellar winds or shock waves. When this happens, regions within the cloud may begin collapsing to form new stars. These interactions link the life cycles of stars, where the activity of one generation influences the birth of another. Stellar winds are streams of charged particles emitted by stars. These winds can travel vast distances and interact with surrounding gas and dust. Over time, they can carve out cavities in interstellar clouds, creating bubble-like structures around stars. The solar wind, produced by the sun, extends far beyond the planets and forms a protective bubble known as the heliosphere. This region interacts with interstellar space at its outer boundary. The heliosphere acts as a shield, reducing the number of high-energy particles that reach the inner solar system. Magnetic fields exist throughout space and influence the motion of charged particles. These fields can guide particles along specific paths, shaping cosmic structures. Although invisible, magnetic fields are essential in understanding how matter moves and interacts in the universe. Shock waves from supernova explosions travel through space, compressing and heating the interstellar medium. These waves can trigger new star formation in nearby regions. At the same time, they distribute heavy elements that become part of future stars and planets. Binary star systems often exchange material when one star expands into a red giant. Gas can flow from one star to the other, forming an accretion disk. This transfer of matter can dramatically change the brightness and behavior of the system. Accretion disks fall not only around stars, but also around black holes and young stellar objects. These disks consist of material spiraling inward under gravity. As the material moves inward, it heats up due to friction, often emitting large amounts of energy. Jets of material can be ejected from the poles of accretion disks at very high speeds. These jets can extend for vast distances into space. They are commonly observed around young stars and active galactic nuclei. Planetary systems are influenced by gravitational interactions between their components. Planets can affect each other's orbits, causing shifts over time. These interactions can lead to stable configurations or, in some cases, instability and ejection of objects. Resonance occurs when orbiting bodies exert regular, periodic gravitational influence on each other. This can stabilize or destabilize their motion. Such resonances are observed in planetary systems, including our own. Asteroids within the asteroid belt interact gravitationally with nearby planets, especially Jupiter. These interactions can alter their orbits. Some asteroids are pushed into paths that bring them closer to Earth. Comets are affected by both gravitational forces and solar radiation. As they approach the Sun, heat causes their icy surfaces to release gas and dust. This process creates the glowing coma and tail associated with comets. The tails of comets are shaped by interactions with the solar wind and radiation pressure. These forces push material away from the Sun. As a result, comet tails always point outward from the Sun, regardless of the comet's direction of travel. The zodiacal light is produced by sunlight scattering off dust particles within the inner solar system. This creates a faint glow visible under dark conditions. It forms a subtle band along the ecliptic, connecting the Sun's path across the sky. Planetary atmospheres interact with solar radiation in complex ways. These interactions can influence temperature, composition, and visibility. They also determine how planets appear when observed from Earth. Auroras occur when charged particles from the solar wind interact with Earth's magnetic field and atmosphere. These interactions produce glowing lights near the poles. The colors of auroras depend on the type of gas and the energy of the incoming particles. The brightness of stars can fluctuate due to internal processes such as pulsations. These changes can occur in regular or irregular patterns. Such variations provide information about the internal structure of stars. The surfaces of stars can experience activity such as flares and spots. These features are linked to magnetic fields and energy release. They can influence the light emitted by the star over time. Stellar rotation can affect how stars distribute heat and energy across their surfaces. Rapid rotation can lead to uneven temperature distribution. This can create differences in brightness between different regions of the star. Galaxies interact gravitationally with one another, sometimes forming tidal tails of stars and gas. These elongated structures stretch out from galaxies during close encounters. They are evidence of past interactions and ongoing evolution. Gas within galaxies can cool and condense, leading to the formation of new stars. This process depends on local density and temperature. Regions with higher concentrations of gas are more likely to produce new stars. The rate of star formation within a galaxy can vary over time. Some galaxies experience bursts of activity, while others remain relatively quiet. These variations are influenced by internal and external factors. Supermassive black holes at the centers of galaxies can influence their surroundings by emitting energy and jets. These outputs can affect star formation. In some cases, they can limit the growth of new stars by heating surrounding gas. Gravitational interactions between galaxies can lead to mergers, combining their stars and gas into a single system. This process reshapes their structure. The resulting galaxy may differ significantly from its predecessors. Dust within galaxies can both obscure and reflect light. This dual role affects how galaxies appear when observed. It can hide certain regions while highlighting others through scattered light. The interstellar medium acts as a reservoir of material for star formation. It is constantly being enriched by stellar processes. This medium connects different stages of stellar evolution. Energy from stars can ionize surrounding gas, causing it to emit light. This creates glowing regions within nebulae. These regions are often associated with young, hot stars. The motion of stars within a galaxy is influenced by its overall gravitational potential. Stars follow orbits that depend on their position and velocity. These motions contribute to the galaxy's structure and dynamics. The night sky includes interactions between radiation and matter at many scales. Light can be absorbed, emitted, or scattered depending on conditions. These processes shape how objects appear and how energy is distributed. The balance between heating and cooling processes determines the state of gas in space. This balance affects whether gas will collapse to form stars. It is a key factor in the evolution of galaxies. Cosmic rays interact with the interstellar medium, transferring energy and influencing chemical reactions. These interactions occur continuously. They contribute to the dynamic environment of space. The formation of molecular clouds involves the cooling and condensation of gas. These clouds are the sites where new stars are born. Their structure is shaped by turbulence, gravity, and magnetic fields. Turbulence within gas clouds creates complex patterns of density. Some regions become dense enough to collapse under gravity. This leads to the formation of stars in clusters or groups. The night sky reflects a network of interactions connecting stars, gas, dust, and galaxies. Each component influences the others. These interactions create a constantly evolving cosmic environment. Even when observed from a distance, these processes leave visible signatures. Changes in brightness, color, and structure reveal underlying activity. The night sky is therefore not static, but a result of ongoing interactions. At the smallest scales within the night sky, matter behaves in ways that are governed by fundamental particles and subtle interactions. Even the light reaching your eyes is composed of photons, tiny packets of energy traveling across vast distances through space. These photons carry information about their origins, including the temperature, composition, and motion of the objects that emitted them, allowing scientists to decode distant phenomena. Within stars, nuclear fusion occurs at the atomic level, where hydrogen nuclei combine under extreme pressure and temperature to form helium. This process releases energy in the form of light and heat. The balance between gravitational compression and the outward pressure from fusion determines the stability of a star over long periods. The atoms that make up stars and planets were formed through nuclear processes in earlier generations of stars. Elements heavier than hydrogen and helium are created in stellar cores or during explosive events like supernova. These elements are later dispersed into space, becoming part of new stars, planets, and eventually everything observed in the night sky. Electrons within atoms absorb and emit light at specific wavelengths, creating spectral lines that act as unique signatures for each element. These lines can be observed in the light from stars. By studying these patterns, scientists can determine the chemical composition of distant celestial objects. At very small scales, the behavior of particles is influenced by quantum mechanics. This governs how energy levels change within atoms and how light interacts with matter. These quantum effects are essential in understanding the radiation emitted by stars and other cosmic sources. The temperature of a star determines the energy distribution of the photons it emits. Hotter stars emit more high-energy light, while cooler stars emit lower energy light. This difference in energy distribution is what gives stars their characteristic colors. The interaction between light and interstellar dust involves scattering and absorption processes at the microscopic level. Dust grains, though tiny, can significantly alter how light travels through space. These interactions shape the appearance of distant stars and galaxies, affecting both brightness and color. Cosmic rays consist of high-energy particles that move through space at nearly the speed of light. These particles can originate from supernova or other energetic events. When they interact with Earth's atmosphere, they produce cascades of secondary particles that can be detected at the surface. Neutrinos are extremely small and weakly interacting particles produced in nuclear reactions, such as those occurring within stars. They can pass through matter almost unaffected. Billions of neutrinos pass through your body every second, yet they rarely interact with anything. Within neutron stars, matter is compressed to densities so high that atomic structures collapse. Protons and electrons combine to form neutrons. This creates a state of matter that behaves very differently from anything found under normal conditions. The strong nuclear force holds atomic nuclei together, overcoming the repulsive forces between positively charged protons. This force operates at extremely short distances. It plays a crucial role in the processes that power stars and create elements. The electromagnetic force governs how charged particles interact with light and each other. It is responsible for the emission and absorption of radiation. This force influences nearly all observable interactions in the night sky. Gravity, though weaker than other fundamental forces at small scales, dominates at large scales. It governs the motion of planets, stars, and galaxies. At the particle level, gravity still plays a role, but its effects are often overshadowed by stronger forces. In regions of intense gravity, such as near black holes, the behavior of particles and light becomes extreme. Light can be bent or trapped entirely. These conditions provide natural laboratories for studying physics under extreme circumstances. Photons traveling through space can be redshifted or blueshifted, depending on the motion of their source relative to the observer. This shift changes their wavelength. This effect provides information about the velocity and direction of celestial objects. The vacuum of space is not completely empty at the quantum level. It contains fluctuating energy fields and virtual particles that appear and disappear. These fluctuations are a fundamental aspect of quantum physics and influence how space behaves. Atoms in interstellar space can combine to form simple molecules, such as hydrogen molecules. These molecules are the building blocks of more complex chemistry. Molecular clouds composed of these particles are key regions for star formation. The temperature of space affects how particles move and interact. At extremely low temperatures, particle motion slows significantly. This environment influences the formation and stability of cosmic structures. Dust grains in space can act as catalysts for chemical reactions, allowing molecules to form on their surfaces. These processes contribute to the chemical diversity observed in the universe. The polarization of light occurs when electromagnetic waves align in a particular direction. This can happen when light is scattered or passes through magnetic fields. Studying polarization helps reveal information about cosmic environments and structures. Charged particles moving in magnetic fields emit radiation known as synchrotron radiation. This process occurs in many astrophysical environments. It is often detected in radio wavelengths and provides insight into energetic processes. The energy levels of atoms determine the specific wavelengths of light they can emit or absorb. These discrete levels are a result of quantum mechanics. Transitions between these levels produce the spectral lines observed in astronomy. In extremely hot environments, atoms can lose electrons, becoming ionized. Ionized gas behaves differently from neutral gas. Such ionized regions are common in nebulae and around hot stars. Plasma, a state of matter consisting of ionized gas, is common throughout the universe. It responds strongly to electromagnetic fields. Much of the visible matter in the night sky exists in this plasma state. The interaction between radiation and matter can exert pressure, known as radiation pressure. This can influence the movement of particles. In some cases, radiation pressure can counteract gravitational forces. The speed of light is a constant in the universe, determining how quickly information and energy can travel. This speed sets a limit on how far and how fast we can observe events in the night sky. Photons can travel for billions of years without interacting with anything, preserving information about their source. This allows observations of very distant objects to provide insights into the early universe. The absorption of light by atoms can create dark lines in the spectrum, known as absorption lines. These lines reveal the presence of specific elements between the source and the observer. Emission lines occur when atoms release energy as light at specific wavelengths. These lines are characteristic of particular elements. They are often observed in glowing nebulae and other energetic regions. The night sky includes phenomena governed by both classical and quantum physics. These frameworks work together to explain observations. Understanding both is essential for interpreting what is seen. The interaction of particles at very small scales underlies all larger cosmic processes. From fusion in stars to the formation of galaxies, these interactions are fundamental. They connect the smallest building blocks of matter to the largest structures in the universe. Observing the night sky relies on the careful measurement of light, often captured through telescopes that collect and focus photons from distant sources. These instruments increase the amount of light reaching the observer, allowing faint objects to become visible. By gathering more light than the human eye can alone, telescopes reveal structures and details that would otherwise remain hidden in darkness. Optical telescopes use lenses or mirrors to focus incoming light. Reflecting telescopes, which use mirrors, are commonly used for large observatories because they can be built at greater sizes. The larger the telescope, the more light it can collect, improving both brightness and resolution of distant objects. Resolution refers to the ability to distinguish fine details in an image. Higher resolution allows astronomers to separate objects that appear very close together in the sky. This is especially important when studying distant galaxies or closely spaced stars. Atmospheric turbulence can blur images seen from Earth, limiting the clarity of observations. This effect is known as seeing. To reduce this, observatories are often placed in high, dry locations where the air is more stable. Adaptive optics is a technology used to correct distortions caused by the atmosphere. It works by adjusting mirrors in real time to compensate for air turbulence. This allows ground-based telescopes to achieve sharper images closer to those obtained in space. Space telescopes avoid atmospheric interference entirely by operating above Earth's atmosphere. This provides clearer and more consistent observations. They can also observe wavelengths of light that are blocked by the atmosphere, such as ultraviolet and X-rays. Radio telescopes detect radio waves emitted by celestial objects. These waves can pass through dust clouds that block visible light. This allows astronomers to study regions of space that would otherwise be hidden. Arrays of radio telescopes can be combined to act as a single, larger instrument. This technique, known as interferometry, improves resolution. By linking multiple telescopes, scientists can simulate a much larger observing area. Infrared telescopes detect heat radiation from objects in space. This allows observation of cooler objects and regions obscured by dust. Infrared observations are especially useful for studying star-forming regions and distant galaxies. X-ray telescopes are designed to observe high-energy radiation from extreme environments, such as black holes and neutron stars. Because Earth's atmosphere blocks X-rays, these telescopes must operate in space. Gamma-ray observatories detect the most energetic radiation in the universe. These observations reveal violent events such as gamma-ray bursts. Such events are often linked to collapsing stars or merging neutron stars. Spectroscopy is a technique used to analyze the light from celestial objects. By splitting light into its component wavelengths, scientists can study its properties. This method reveals information about composition, temperature, and motion. Spectral lines act as fingerprints for elements, allowing identification of materials in stars and galaxies. Each element produces a unique pattern, making it possible to detect even small amounts. The Doppler effect is used to measure motion in the night sky. When an object moves toward or away from the observer, its light shifts in wavelength. This shift provides information about the speed and direction of the object's motion. Photometry measures the brightness of celestial objects over time. This technique is used to study variable stars and detect exoplanets. Changes in brightness can reveal underlying physical processes. Exoplanets are often detected using the transit method, where a planet passes in front of its star and causes a slight dip in brightness. This method allows astronomers to determine the size and orbit of the planet. Another method for detecting exoplanets is the radial velocity technique. It measures the wobble of a star caused by the gravitational pull of an orbiting planet. This wobble can be detected through shifts in the star's spectral lines. Astrometry involves measuring the precise positions of stars. Small changes in position can indicate the presence of unseen companions. This technique is useful for detecting planets and studying stellar motion. Parallax is used to measure distances to nearby stars. By observing a star's apparent shift against distant background stars, its distance can be calculated. This method provides one of the most direct measurements of distance in astronomy. Standard candles are objects with known brightness, such as certain types of variable stars or supernova. They're used to measure distances to faraway galaxies. By comparing their known brightness to how bright they appear, distances can be estimated. Gravitational lensing can also be used as a measurement tool. By analyzing how light is bent around massive objects, astronomers can infer mass and structure. This technique reveals information about both visible and dark matter. Domain astronomy focuses on changes in the night sky over time. Observations are repeated to detect variability and transient events. This approach has led to the discovery of phenomena such as supernova and gamma-ray bursts. Large sky surveys systematically map the night sky, recording the positions and properties of millions or billions of objects. These surveys create detailed catalogues that support a wide range of research. Charge-coupled devices, or CCD, are electronic detectors used in modern telescopes. They are highly sensitive to light and can capture faint signals. CCDs have largely replaced photographic plates due to their efficiency and accuracy. Calibration is essential in astronomical observations. Instruments must be carefully adjusted to ensure accurate measurements. This includes correcting for factors such as background noise and instrumental effects. Noise in observations can come from various sources, including electronic interference and background radiation. Reducing noise improves the reliability of data collected from the night sky. Data from telescopes are often processed using computers to extract meaningful information. This processing can involve filtering, enhancing and analyzing signals. Astronomers use models and simulations to interpret observational data. These models help explain how physical processes produce observed patterns. They are essential for understanding complex systems. Observations are often repeated to confirm findings and reduce uncertainty. Consistency across multiple observations increases confidence in results. International collaborations allow observatories around the world to share data and resources. This global effort enhances the study of the night sky. Some observatories operate continuously, monitoring the sky for transient events. This constant observation increases the chances of detecting rare phenomena. Citizen scientists also contribute to observations by analyzing data or making independent discoveries. Their involvement expands the reach of astronomical research. Space missions are designed to study specific objects or regions in detail. These missions provide close-up data that complement observations from Earth. Instruments aboard spacecraft can measure properties such as magnetic fields, particle flux, and radiation. These measurements provide insights into environments that cannot be replicated on Earth. The detection of gravitational waves requires highly sensitive instruments capable of measuring tiny distortions in spacetime. These detectors open a new way of observing the universe. Multi-messenger astronomy combines observations from light, gravitational waves, and particles. This approach provides a more complete understanding of cosmic events. The night sky is studied across many wavelengths, each revealing different aspects of objects. Combining these observations creates a fuller picture of the universe. Advances in technology continue to improve the ability to observe the night sky. New instruments and methods expand what can be detected and measured. The process of observation is ongoing, with new discoveries continually being made. Each observation adds to the collective understanding of the cosmos. The human experience of the night sky begins with the eye's ability to adapt to darkness, a process known as dark adaptation. In low-light conditions, the eye gradually shifts from relying on cone cells, which detect color, to rod cells, which are more sensitive to faint light. This adaptation can take up to 30 minutes to fully develop, allowing the observer to detect much fainter stars and subtle features that are otherwise invisible in brighter conditions. Rod cells in the human eye are highly sensitive to light, but do not perceive color in the same way cone cells do. This is why most stars appear white or slightly gray to the naked eye. Only the brightest stars show hints of color, such as a faint reddish or bluish tint, depending on their temperature and brightness. Peripheral vision is often more effective than direct vision when observing faint objects in the night sky. This is because rod cells are more concentrated away from the center of the retina. By looking slightly to the side of a faint object, it can become more visible, a technique commonly used in stargazing. The brightness of the moon can significantly affect night vision. Even a partially illuminated moon can reduce the visibility of faint stars. This occurs because the increased light prevents the eyes from fully adapting to darkness. Artificial light sources have a similar effect on human vision. Exposure to bright light can quickly reverse dark adaptation, reducing sensitivity to faint objects. Even brief exposure to a bright screen or lamp can impact the ability to observe the night sky clearly. The perception of the sky's color changes with light conditions. Under very dark skies, the sky can appear deep blue or even slightly greenish, rather than completely black. This subtle coloration is influenced by airglow and scattered light in the atmosphere. Human perception can also create visual illusions in the night sky. The moon illusion, for example, makes the moon appear larger near the horizon than when it is overhead. This effect is caused by the brain interpreting distance and scale rather than any actual change in size. The apparent motion of stars can create a sense of slow movement across the sky, which may be perceived differently depending on how long one observes. Over extended periods, this motion becomes more noticeable as stars shift position relative to landmarks. The ability to recognize constellations depends on pattern recognition within the human brain. Familiar shapes are identified from the arrangement of stars. Different cultures have created different patterns from the same stars, reflecting variations in interpretation. The brightness of individual stars can influence how easily patterns are recognized. Brighter stars tend to form the main points of constellations. Fainter stars fill in the surrounding areas, contributing to the overall pattern. Human vision is limited in detecting faint light compared to modern instruments. Telescopes and cameras can reveal objects far beyond what the eye can see. This difference highlights the role of technology in extending human perception. The night sky can appear sharper in colder conditions, as cooler air tends to be more stable and less turbulent. This stability reduces the distortion of light, improving clarity for observers. Humidity can affect how the sky appears by scattering light and reducing contrast. High humidity can make the sky look hazy. Dry air, on the other hand, often provides clearer views with greater visibility of faint objects. The human brain processes visual information from the night sky in a way that emphasizes contrast and edges. This processing helps distinguish stars from the darker background. The sensation of depth in the night sky is limited because all objects appear projected onto a two-dimensional surface. Despite this, knowledge of distance can create a conceptual sense of depth. The perception of brightness is influenced by surrounding light levels. In darker environments, stars appear brighter and more numerous. This is due to the increased sensitivity of the eye in low-light conditions. Color perception in low light is reduced, making it difficult to distinguish subtle differences in star color. Only the most intense colors are noticeable without optical aid. The human eye is capable of detecting motion, which can make moving objects like satellites or meteors stand out against the static background. This sensitivity helps identify transient events in the sky. Meteors are often perceived as sudden flashes because they move quickly across the field of vision. Their brief duration contrasts with the steady presence of stars. The night sky can evoke a sense of scale that is difficult to fully comprehend. The vast distances involved are beyond direct human experience. This perception is shaped by both visual input and knowledge of astronomical distances. Astronomical observations rely on instruments to extend beyond human sensory limits. These tools detect wavelengths of light that the eye cannot perceive. This allows for a more complete understanding of the universe. Infrared observations reveal heat signatures, while radio observations detect long wavelength signals. Each type of observation provides unique information. Human hearing is not directly involved in observing the night sky, but sound can influence the experience by providing environmental context. Quiet surroundings can enhance focus on visual observation. The night sky experience is influenced by environmental factors such as temperature, wind, and light pollution. These factors can affect both comfort and visibility. The brain integrates sensory information to create a coherent perception of the sky. This integration helps interpret patterns and motion. The perception of time can change while observing the night sky. Extended observation may make time feel slower or more continuous. This effect is influenced by the gradual motion of celestial objects. The night sky can be used as a reference for orientation and navigation. Recognizing patterns allows individuals to determine direction. This skill has been used historically for travel and exploration. The brightness of planets compared to stars can help distinguish them visually. Planets often appear steadier and brighter. This difference is due to their proximity and apparent size. The human eye can detect only a fraction of the electromagnetic spectrum. Most radiation from the universe is invisible to us. Instruments are required to observe these hidden wavelengths. The perception of the sky can change with altitude. Higher elevations provide clearer views due to reduced atmospheric interference. This improves visibility and detail. The night sky is often perceived differently in urban versus rural environments. Light pollution reduces the number of visible stars. In darker locations, the sky appears richer and more detailed. The experience of observing the night sky is influenced by expectations and prior knowledge. Familiarity can enhance recognition and interpretation. Learning about the sky can change how it is perceived. The brain can fill in gaps in visual information, creating continuous patterns from scattered points of light. This ability helps form constellations and recognize shapes. The perception of brightness can be affected by adaptation to darkness. Over time, more stars become visible. This gradual change enhances the viewing experience. The night sky can appear different depending on the observer's location on Earth. Latitude affects which stars are visible. This creates variation in the sky's appearance across the globe. The visual experience of the night sky is shaped by both physical and psychological factors. Light, atmosphere, and perception all play roles. Together, these elements define how the sky is seen. The night sky changes slowly over long periods due to the gradual motion of stars through space, a phenomenon known as proper motion. Although these movements are extremely subtle, they accumulate over thousands or millions of years. Over long timescales, constellations slowly change shape as their component stars shift relative to one another, altering patterns that once appeared fixed. The rotation of Earth is not perfectly constant and can vary slightly over time. These small changes are influenced by factors such as tidal interactions with the Moon. As a result, the length of a day is gradually increasing, though the change is only noticeable over very long periods. The Moon is slowly moving away from Earth at a rate of a few centimeters per year. This recession is caused by tidal interactions between the Earth and the Moon. Over millions of years, this will affect the apparent size of the Moon in the sky. The precession of Earth's axis causes a slow shift in the orientation of the night sky. This motion alters the position of the celestial poles over time. As a result, the identity of the North Star changes across thousands of years. The positions of the equinoxes also shift due to precession. This gradual movement affects the timing of seasons relative to the stars. Over long periods, this shift changes how constellations align with seasonal events. The orbits of planets can change slightly due to gravitational interactions with other bodies. These changes occur over long timescales. Such variations can influence the stability and configuration of planetary systems. The brightness of stars can evolve as they age and move through different stages of their life cycle. Some stars become brighter, while others fade. These changes are gradual and often occur over millions or billions of years. The structure of galaxies evolves as stars form, age, and die. Gas is converted into stars, and stellar remnants accumulate. This ongoing process changes the appearance and composition of galaxies over time. Galaxies can also change through interactions with other galaxies. Collisions and mergers reshape their structure. These processes occur over billions of years and can significantly alter galactic forms. The Milky Way itself is evolving, slowly absorbing smaller galaxies and redistributing their stars. Evidence of this can be seen in streams of stars moving through the galaxy. Star clusters gradually disperse as gravitational interactions pull stars away from their original group. Over time, these clusters become less distinct and eventually blend into the general stellar population. Globular clusters, while more stable, also experience slow changes. Their stars move within the cluster, and some may escape over time. Despite this, they remain bound for very long periods. The interstellar medium changes as gas is consumed in star formation and replenished by stellar winds and supernova. This balance between consumption and replenishment shapes the evolution of galaxies. The rate of star formation within a galaxy can increase or decrease over time, depending on available material and environmental conditions. Periods of intense star formation may be followed by quieter phases. Supernova remnants expand gradually into surrounding space, cooling and dispersing over time. These remnants can persist for thousands of years before fading. The distribution of heavy elements in the universe increases over time as stars produce and disperse them. This enrichment allows for more complex structures to form in later generations of stars. Planetary systems can evolve as gravitational interactions shift orbits. Some objects may migrate closer to or farther from their star. These changes can affect the long-term stability of the system. Asteroids and comets can experience slow orbital changes due to gravitational influences and interactions with other bodies. These changes can alter their paths over long periods. The surfaces of planets and moons can change gradually due to impacts, geological activity, and atmospheric processes. These changes are often subtle but accumulate over time. The brightness of the night sky can vary slightly due to long-term changes in atmospheric composition. Natural events such as volcanic eruptions can influence these variations. Light pollution from human activity has increased over time, reducing visibility of the night sky in many regions. This change has occurred over decades rather than millennia, but still affects observation. The sun itself evolves slowly, increasing in brightness over billions of years as it ages. This gradual change will influence conditions in the solar system. The solar system moves through different regions of the Milky Way over time. These regions can have varying densities of stars and interstellar material. The cosmic microwave background remains nearly constant, but slowly cools as the universe expands. This cooling reflects the long-term evolution of the universe. The expansion of the universe continues, increasing the distances between galaxies. Over time, this expansion will make distant galaxies less visible. Gravitational interactions between galaxies can alter their motion and structure over long periods. These interactions contribute to the dynamic nature of the universe. The night sky we observe today is different from what was seen by ancient observers due to gradual changes in positions and brightness. These differences accumulate over long timescales. Future observers will see a different night sky as stars move and galaxies evolve. The patterns we recognize today will eventually change. The concept of constellations is therefore temporary on cosmic timescales. Their shapes are not permanent, but evolve slowly over time. The alignment of stars within constellations is a result of perspective from Earth. In three-dimensional space, these stars may be widely separated. The visibility of certain objects can change due to long-term variations in brightness or position. Some objects may become more prominent, while others fade. The night sky reflects a balance between stability and change. While it appears constant over short periods, it is dynamic over long timescales. The processes that shape the sky operate continuously, even when not immediately noticeable. These slow changes contribute to the ongoing evolution of the universe. The passage of time reveals new aspects of the sky as objects move and change. This gradual transformation is part of the nature of the cosmos. The night sky serves as a record of both past and ongoing processes. Each observation captures a moment within this long timeline. The night sky continues its quiet motion even when it appears still, with stars tracing slow, predictable paths that repeat night after night. This steady movement is a reflection of Earth's rotation, carrying the observer gently beneath a vast, shifting canopy. Over the course of hours, these motions unfold gradually, forming arcs that rise, curve, and descend, maintaining a rhythm that remains consistent across time. Some stars remain visible throughout the entire night, circling the celestial pole without ever setting below the horizon. These circumpolar stars move in continuous loops, never disappearing from view. Their constant presence creates a sense of stability within the sky as they trace the same paths again and again with quiet precision. The faint glow of the Milky Way stretches softly across the sky, its structure shaped by the distribution of stars and interstellar material within the galaxy. This glow is not uniform, but gently varied, with brighter regions and darker lanes. These subtle differences form a textured band that perfects the complex arrangement of stars, gas, and dust within the galactic disk. Even in the darkest conditions, the sky is never completely black. Airglow and scattered light create a gentle background illumination that softens the contrast between stars and space. This faint brightness is constant, a quiet presence that exists even when it is barely noticeable. The light from distant stars travels uninterrupted across space for years, centuries, or longer, maintaining its path until it reaches Earth. During this journey, it carries information about its origin. When it finally arrives, it becomes part of the quiet pattern of light that defines the night sky. Planets move slowly against the background of stars, shifting position from night to night in a steady progression. Their motion is subtle but continuous. This gradual movement reflects their orbits within the solar system, unfolding at a pace that becomes clear only over time. The phases of the Moon change in a regular cycle, reflecting the changing angle between the Sun, Earth, and Moon. This cycle repeats over approximately a month. Each phase alters the brightness and appearance of the Moon, influencing how the rest of the sky is perceived. The presence or absence of moonlight affects how many stars are visible. On darker nights, more stars can be seen as the eye adapts fully to low light. This variation creates a natural rhythm in the visibility of the night sky. The sky remains consistent in its large-scale structure, even as individual objects move and evolve. The patterns formed by stars change slowly, but the overall arrangement persists. This balance between motion and stability gives the sky its enduring character. The night sky includes regions of calm where little change is visible over short timescales. These areas provide a steady backdrop for observation. Against this stillness, subtle movements and variations can be gently noticed. Light from galaxies beyond the Milky Way contributes to the overall brightness of the sky, even when those galaxies are not individually visible. This faint background light is a collective presence, formed from countless distant sources. The cosmic microwave background fills all of space with a nearly uniform radiation, a quiet remnant of the universe's early state. Though invisible to the eye, it exists as a constant feature of the cosmic environment. The temperature of space remains extremely low, with only slight variations across vast distances. This uniformity reflects the large-scale conditions of the universe. It provides a stable backdrop against which other processes occur. The motion of the solar system through the galaxy is steady and continuous, carrying it through different regions over long timescales. This motion is imperceptible in the short term but contributes to the evolving perspective of the night sky. Stars continue to form within distant clouds of gas and dust, even as older stars fade and disappear. This ongoing cycle maintains the balance of creation and decay. It unfolds quietly, without interruption, across the galaxy. Supernova remnants expand slowly into space, their energy dispersing over time as they blend into the surrounding medium. These remnants gradually fade, leaving behind enriched material for future generations of stars. The interstellar medium remains in constant motion, shaped by gravity, radiation, and magnetic fields. Its structure changes gradually over time. This slow evolution influences where and how new stars will form. Galaxies drift through space, their motions governed by gravity and the expansion of the universe. Their positions change slowly over billions of years. These movements reshape the large-scale structure of the cosmos. The expansion of the universe continues at a steady rate, increasing the distance between galaxies. This process unfolds uniformly across space. Over time, this expansion alters what can be observed from any given point. The light reaching Earth at any moment represents a blend of many different times and distances. Some photons began their journey recently, while others have traveled for billions of years. Together, they create a continuous flow of information from across the universe. The night sky is shaped by processes that operate across vast scales, from atomic interactions to galactic motion. Each scale contributes to the overall experience. These processes work together in quiet coordination, forming a unified view. The patterns seen in the sky are not permanent, but evolve slowly as stars move and systems change. This transformation is gradual and ongoing. Over long periods, familiar arrangements shift, revealing new configurations. The sky remains a consistent presence, even as its details change. Its motions are steady, and its processes unfold without interruption. This continuity provides a sense of calm within its vast complexity. The act of observing the night sky connects the present moment with distant events. Each observation is a meeting point between now and long ago. This connection is created through the travel of light across space. The quiet nature of the night sky reflects the balance of forces at work. Gravity, radiation, and motion coexist in a stable arrangement. This balance allows the sky to appear calm despite its constant activity. The night sky does not require attention to exist. It continues its patterns regardless of observation. Its processes are independent and ongoing. Whether seen or unseen, it remains active and unchanged in its rhythm. The gradual movement of celestial objects creates a sense of continuity over time. Each night follows from the last, with subtle differences. This progression is smooth and uninterrupted. The sky above is part of the larger universe that extends beyond what can be observed. Much remains unseen, beyond the limits of detection. Yet what is visible offers a glimpse into this greater expanse. The light that reaches Earth is only a small portion of what exists. Many forms of radiation are invisible to the human eye. Despite this, they contribute to the overall structure and behavior of the universe. The night sky reflects a steady flow of energy and motion. Even in stillness, processes continue across all scales. This quiet activity defines the nature of the cosmos. And as the hours pass, the sky continues its gentle turning, carrying each star along its path, holding its place in a vast and steady rhythm where everything moves slowly, quietly, and without end.